Hello, math magicians. On this beautiful day, we're going to be looking at section 3.4 called Arithmetic Sequences. Arithmetic. So usually we say arithmetic if we're talking about it as a noun, but here it's an adjective. So arithmetic sequence. So we're going to identify and describe what arithmetic sequences are. So by way of warm-up, take a gander over here. We've got this fabric that is being designed by a fashion designer, shockingly so. So let's go ahead and figure out, based on the row numbers right here, and the darker ones are the shaded squares in the row. So go ahead and take a moment to fill those out. And what patterns do you notice? What patterns do you see from the row number to the shaded, and then the row number maybe to the total number? So take a moment and do that. So check your answers here as we count them up. And now the key, of course, is the pattern. Notice the number of shaded squares goes up, two, up, two, up, two, up, two. So every row, we're adding two more. So there's a pattern. Well, notice what this is here. The number of total shaded, so that's so 4 plus 3 plus 2 plus 1. What do we get? Well, this is going up 3, up 5, up 7, up 9. And where do you see those ups? Right here. These numbers there. So it's almost as if the pattern here becomes the pattern of the pattern, becomes the pattern of the sum. Another thing to notice, these are all perfect squares. All right, so let's use some vocabulary today and get you into arithmetic sequences. Is the ordered list 26, 39, 52, 65, 78 an arithmetic sequence? But before we can know that, we have to know what a sequence is. So a sequence is an ordered list of numbers that form a pattern. Now, we don't know what kind of pattern it could be, because above we saw two types of patterns. One where the pattern was the same, and another where the pattern had a pattern too. So each number is called a term. So this right here is the first term. This one here is my second term, and my third, etc. And of course, clearly that's my fifth term. However, an arithmetic sequence has a pattern that's between the consecutive terms, that is addition, or if you're adding a negative, that's subtraction. So you can go up or down. All right, if you didn't know what consecutive means one after another. So in order, with a pattern. So for example, these are consecutive numbers, 1, 2, 3, 4. A, B, C, D are consecutive letters, etc. All right, so the question is, again, is this right here, is this an arithmetic sequence? So that means, is the distance between the terms the same? So the common difference here, let's see, to get from the 26 to the 39, I add 13. And from here, I add 13. Oh, there we go. Good. So we're adding 13 each time. So because the pattern is true for the whole time, the common difference is 13. And that's what one adds to get to the next number in the sequence. Add 13. Add 13. Every time. And notice the common difference. Why is it called a difference? Well, because if you take 39 and minus 26, or if you take 52 and minus 39. So all you did was take 1 minus the previous. All right, we can also think of each sequence as a function based on the number of terms. The domain is restricted, of course, to just these types of numbers here, to the whole numbers. Or we'll call it the natural numbers. And the range is the terms. Okay, so in function notation, we can write it like this. So let me just clarify here. If we did write it, my first term is 26, my second term is 39, etc. So my fifth term is 78. If this was called my function, a of n, then in function notation, we say a of 1 is equal to 26. And a of 2 is 39, and etc. Another way we write that is with called subscript notation. And we just write like this. A with a small 1 down below is 26. And so we just call this my first term is 26. Continuing on, my second term with a small 2 is 39. And I can go all the way to my fifth term, which is 78. Now notice what this does not mean. So a sub 2, also simply called a2, does not equal a with a big 2 like that, and still it doesn't equal a with a square. So each of these means something else. This isn't a term number, an order, and doesn't affect the actual a. This one does. It says double the a, and this one says square the a. So these are operations, and this is a name. It's an identifier. All right, so let's see here. Now it's your turn. Given this pattern, what is the common difference? What's the fifth term in the subscript and function notation? So pause, try it, and check your answer. And check your answer. Now that we've defined arithmetic sequence, what we're going to do is use that information in order to create formulas. So we're going to look at what's called recursive and explicit formulas. So first one, recursive. The word recursive simply means to repeat over and over again. So this formula, what it does is it relates each new term to the previous term. So let's just look at this right here. It's funny notation, but an equals an minus 1 plus d. So what is each of these things here? This is my desired term, the term that we want. I want the 16th term. I want the 23rd term. So that's what that one is. Next, this one here is my previous term. So if I'm looking for the 30th term, then this one is my 29th term. And lastly, the d is my common difference. Now this is a very helpful one to generate a sequence. But it's not very helpful if I'm looking for the 30th term. Let's walk through this example here. So 26, 39, 52, 65, and 78, we want to find the 15th term. So recursively, this is what I do. Let's start with just finding the formula. So a sub n minus, and then a n minus 1. And we already know what d is, right? Because we already calculated it, 13. So here I say plus 13. Now, this doesn't help. Why? Because before I can find the 30th term, I have to find the 29th term. But before I can find the 29th term, I have to find the 28th term, etc. So I need to give another piece of information. Where do I begin? Where's the process all start? So I do have to start at my first term at 26. So essentially what this is saying is, to find your term, you need the previous term and add 13. My starting is 26. So I could generate the entire sequence here. 26 plus 13 is 39. Then the next one, third term, is 52, etc. And then counting out to 15 is a lot of work. So that's why the recursive is not super helpful right here. So I'm not going to find the 15th term, for it's too much work. So let's look at explicit now. This formula helps one to find the nth term using not the previous term, but the first term. And this corresponds roughly to slope-intercept form. So this is what it looks like. And we read it like this. an equals a1, first term, plus n minus 1 times d. So let's define each of these. So let's see where this comes from. This is my desired term, this is my first term, and this is my common difference. But notice, what's this n minus 1 stuff? Well, if we were to count terms, this is the number of d's that come between the first term and the desired term. So let's just look real quick over here. Notice, from the first term to the fifth term, how many d's do I have? 1, 2, 3, 4. How many hops do I make? I make 4 hops. To find the fifth term, I make 4 hops. So there we go. We just take my first term and do 13 once, twice, thrice, and 4 times. So it's 4 d's, 4 13s. So let's go ahead and substitute things in. A sub n, I still don't know. My first term, though, is 26. I can plug that in. N minus 1, and I forgot a plus there, times d, which is positive 13. Now I'm going to distribute that 13 into both of those terms there. So an is equal to 26 plus 13n minus 13. And finally, when I simplify, I get this. 13n plus 13. So this is the explicit formula. This is the explicit formula, simplified. Now, if I wanted to find out what the 15th term is, I say a sub 15, or simply a 15, and we do 13 times 15, and then we subtract 13, and we get our final answer. And we get 182. So I don't have to count all the terms to get to 182. I can just substitute in. So there we go. These are the differences between recursive and explicit formula. All right, now it's your turn to do the recursive formula and explicit formula for this pattern. So pause and then come back to check. Now check your answer. Our first term is 4. Our common difference is 4. So when I substitute here, we get a sub n is my previous term plus 4. My first term is 4. Over here, when I substitute in 4 here and 4 there, everything reduces to a sub n equals 4. In other words, this is simply just 4 times whatever term number. My term number 1 is 4. My term number 2 times 4 is 8. My term number 3 times 4 is 12. And lastly, so that means my 10th term is just 4 times 10, 40. Last thing we want to do is look at it sort of an application. So you open a savings account with $400 deposit, and each month after that, you deposit $25. Write a recursive rule and an explicit rule to represent the amount of money you deposited in your savings account. How much money will you save in the account on month 12? All right, a couple things to notice. This is where I start. So there's my A1. This is my common difference because that's how much I'm adding every month. So what do I do with that? Well, A1 is 400 and D is 25. So recursively, AN is equal to AN minus 1 plus 25. And where do I start? A1 is 400. Okay, now what about my other one? So AN is equal to A1 plus the n minus 1 times D. So let me just substitute some things in. AN is equal to my first amount plus n minus 1 times D, and we're told 25 is the common difference. So I'm going to distribute that here and here. So AN is equal to 400 plus 25n minus 25. So here's my formula to find out how much money I have on any given month. Is going to be 25n plus 375. So that's my explicit formula. This is my recursive formula here. And lastly, how much money will you have on month 12? So what I'm going to do is just use that information to say, well, A12. So it's 25 times 12 plus 375. And in the end here, we get $675 on month 12. And there we go. Now it's your turn here to give this one a whirl. And now we check our answer here. Pause. Have a great day.